Okay, hello. We are going to go over one word problem in this video. I'm going to share my screen. We're going to look at homework 5-2. I'm sharing my screen here. Hopefully you can see this. I don't know what I just did, so let me go back there. And we're going to start with this problem, question 16. Okay, question 16. So question 16 for my screen might be question 14 or question 20 for you. So I'm going to go over this one with these numbers, but might look different on your side. So Manuel, with my accent, rode 30 miles downstream in 3 hours. I'm just going to read it. The trip back, however, took him 10 hours. Find the rate that Manuel rose in still water. So this will be if the water is not moving, because it looks like it's moving, as we'll talk about, because he took 3 hours one way, 10 hours the other way. So it looks like the water is helping him in one direction and affecting him to take longer in the other direction. So in still water and the rate of the current. So here the question doesn't ask, when you try to put in the answers, you have downstream equation and upstream equation. So you don't actually need to give the rate that he rose in still water and the rate of the current, but we'll set up the equations that are needed. You could get there. If X is Manuel's rowing speed and Y is the speed of the river current, construct one equation modeling his downstream trip and one modeling his upstream trip. So I will do that on an iPad, share my screen too. I just want to reread this in my own way. And before we do that, here is Roger. He's participating. He's here all the time. It's saying that Manuel, and we're going to assume, someone asked this question before, we're going to assume that he has the same velocity, right? Excluding what's happening with the water. He has the same velocity or speed. Speed will be the magnitude of the velocity in each direction, right? So it says 30 miles in one direction. It took him 3 hours. Then he was rowing in the opposite direction, the same distance. It took him 10 hours. So we're going to use the rowing speed of Manuel and the speed of the river current, which is helping him to row faster in one direction than the other. I'm going to draw that. I'm going to write down the equations and hopefully that helps. Okay. So now I'm going to share my iPad so we can solve that. And sometimes it takes a while, so bear with me here. Oh, I don't want to, come on. Screen mirroring. My bad. I don't know what happened there. All right, that's problem 1, which again is 16 on my screen and might be something different on yours. So we already read the problem statement. So let's start setting it up. I'm going to call the rowing speed X. Let me see if and Y the speed of the river current. Okay, so I'm just going to use the variables that were given in the problem. This is the rowing speed. And Y is the speed of the river current. We take an exam with a problem that's similar and it doesn't ask you to call it X or Y, you call it any variable that you want. Now I'm going to start writing down information that I got from the problem statement. It tells me that downstream, okay, he traveled 30 miles in 3 hours. And then upstream, 30 miles in 10 hours. So I'm going to write that down. I'm going to draw something because it helps me. So I'm going to write over here downstream. So in one direction, the distance was 30 miles, and that happened in 3 hours. So I'm going to draw him. Okay. And I'm going to say that this is his rowing speed, X. Hopefully this doesn't take more than 10 minutes, but we'll see. And I'm trying to figure out if the current was helping him or helping him or hurting him. So I'm going to start writing down information about upstream and see what happens. For upstream, he traveled 30 miles in 10 hours. So he struggled more in that other direction. Okay. Right? So it looks like the river current is in this direction. Hopefully that makes sense. It means I'm moving towards you and you are pulling me in that direction. It will be faster than if I'm moving towards you and you're pushing me away. Okay? For the upstream case, let me see. This is what we did. Upstream case, then the current is still in this direction. Okay? So the total speed of my system here, the total speed is x plus y for this one, for downstream, versus, and this will be in the direction that he's traveling, versus the total speed in the direction that he's traveling is x minus y. X minus y, because I have x, right, moving in that direction, that speed, and I'm subtracting this speed that's working against me, okay? So that's the total speed, and I know the total distance, so we may remember from our lecture that distance is equal to speed multiplied by time. Therefore, he traveled 30 miles in the first trip, where the total speed is x plus y. Again, he's moving with a speed which is different in the number of it. It's different. The number is different, but the speed of the water, the velocity of the water, because now it has direction, is moving and helping him move faster, versus when he's traveling back. He's traveling back, the water is pushing him back. So it takes him longer. So in the other direction, he's still moving 30 miles, but his speed is x minus y. And this one took him 10 hours versus this one took him 3 hours, okay? And then we can use substitution or elimination or whatever you want to use to solve this, because we have two unknowns and two equations. So again, I just want you to see here, let's look at, conceptually what's happening. In one direction, he took less time because the water is helping him. In the other direction, he took longer to travel the same distance because the water is working against him. So then we say the total speed, because we're looking at direction as well, will be x plus y, right? His rowing speed, so we call that rowing speed, plus the speed of the water. It helped him reach, his destination. In the other direction, he's rowing against the water. So we got to subtract it. So it makes sense, the bottom part, just not thinking about the class anymore. If he's moving x, right, the speed x in this direction, right, that bottom part, the one that's highlighted in green, and the water is actually moving faster, then he's gonna end up moving in the direction that he doesn't want to go. That hopefully makes some sense to us. Okay, all right, so let me know if you have any questions, and there I am, and then now I just stop recording. Thank you.